Hi guys, today we are going to be talking about zeros of a polynomial. To be more specific, we are going to be focusing or talking about the multiplicities of a zero. So first, let's go ahead and start it off with the fundamental theorem of algebra. So the fundamental theorem of algebra says that every polynomial of degree greater than 0 or of at least 1 has at least one zero. So whatever the degree is, that is we determine how many zeros we are expected to have. So say if we have a polynomial p of x equals x squared plus 1, the degree is 2, so we're expected to have 2 zeros. If the degree is 4, then we're expected to have 4 zeros, and so forth. Now to get to today's topic, or part of the topic, is multiplicity. Multiplicity tells us how many times a zero appears. So let's go ahead and illustrate that with this quick example. Okay, so the polynomial is right there, the answers are right there, but we're going to pretend that they're not there. So suppose that we are asked to find the zeros of this polynomial. Lucky for us, it's already in factored form. So when we set it equal to 0, what will the zeros be? If this first factor equals 0, that's going to lead to a 0 of -1. I'll show my work in a later example. If the second factor equals 0, I'm going to try to make this unnecessarily longer, okay? So if the second factor equals 0, how's it going to go down? So I'm going to write this without the exponent of 2. So we're going to write 2 times the base, okay? So in this case, the first factor will give us a 0 of 1. The second factor, surprise, will give us a 0 of 1. But when the 0 recycles itself, it's a little redundant, okay? So what we do, we'll say 1 is a 0 recycled twice, or we'll say with the multiplicity of 2. Okay, so multiplicity refers to the number of times that the 0 appears. And for the third factor, so we have 5 factors of x minus 3. Again, I'm gonna do this unnecessarily longer, okay? So let's go ahead and write it with the exponent. So if the exponent is 5, that means that we have 5 factors of the base. Remind me not to pick such large exponents to illustrate my point. I don't want you to do it like this. 1, 2, 3, 4, 5 equals 0. Okay, so if we write it without the exponent of 5, that's going to lead to a 0 of 3. How many times? You said it, 5 times. Sorry for the sloppy work. I don't know why I'm writing so sloppy today. Okay, maybe I'm distracted by all the construction around my house. So I don't think that you hear the construction sound in the video, but it's really loud. Okay, so in this case, when we take x minus 3 raised to the 5th power and set that equal to 0, that's gonna lead to a 0 of 3 recycled 5 times. So there's no need to write it all 5 times. So we say x equals 3 with the multiplicity of 5. So when you write this down, then you're telling the reader, oh, okay, I get it. 3 is a 0 recycled 5 times. Okay, one fancy words, multiplicity, the number of times a 0 appears, is referred to as the multiplicity of a 0. So sorry for the redundancy. So yeah, okay, so the question is, okay, so we had said that 1 is a 0 with the multiplicity of 2, 3 is a 0 with the multiplicity of 5. How come we don't give special love to -1? The reason is because -1 is a 0, but we only see it one time. If you want to use the word multiplicity, then we say -1 is a 0 with the multiplicity of 1. But the only zeros that we give a shout out to is if the multiplicity is higher than 1. Okay, so if it just appears once, then that's it, nothing special. But if it appears more than once, then we give it a shout out and we say, okay, we have a 0 with the multiplicity of 2, 3, 4, 5, and all that good stuff. So let's go ahead and look at a fun problem which may or may not be on your test. So it says identify the degree of the polynomial and then find all zeros, real and imaginary, and indicate their multiplicity if greater than 1. It's really up to you in terms of the degree if you want to answer now or answer later. We're going to answer later with your permission. Okay, so lucky for us that this polynomial is in factored form. So let's go ahead and set it equal to 0. Okay, so if a product equals 0, then one of these factors has to equal 0. So either the first factor equals 0, or the second factor equals 0, or the third factor equals 0, or the fourth factor equals 0. So if the first factor equals 0, we take our time. After we subtract 1 for both sides, that will give us 2x equals -1. And after we divide both sides by 2, that will give us x equals -1/2. Fantastic. For the next equation, we're not going to rewrite it without the exponent. We have no time for that. So what I'm going to do, I'm just going to circle the exponent just to remind myself to write down the multiplicity. So the base is x minus 5 equals 0. And after we add 5 to both sides, that will lead to a 0 of 5. Bear in mind that the base was being raised to the third power, so we want to tell the reader that 5 is a 0 with the multiplicity of 3. So remember, we only give it a shout out if the multiplicity is higher than 1. If the next factor equals 0, so let me go ahead highlight that exponent so I can write down the base once. So that will lead to a 0 of -3. With the multiplicity of 2. Why? Because the exponent is 2. If you really wanted to see it, then you can do it the very long way how I did it earlier. Rewrite it so the base is not being raised to an exponent, but this is a very tedious process even if the exponent is just 2. Cool. Fantastic. If the fourth factor equals 0, let's go ahead and use the square root method. We're going to isolate the squared part. And that will give us x squared is equal to -16. When we apply the square root property to undo the square, let's go ahead square root both sides and insert our plus or minus. As you can see, actually I'm speaking too fast. So on the left side, the square and the square root undo each other, and that will leave us with the radicand of x equals plus or minus whatever the square root of -16 simplifies to. So I'm going to go ahead and do a thinking area. If you can do it mentally, please be my guest. First things first, we want to make sure that the radicand is positive. So we're going to replace the square root of -1 with the imaginary unit I, and then multiply it by the leftover radical, which is square root of 16. Square root of 16 will give us 4, and product of I and 4 is 4i. So that will give us x equals positive or -4i. Something that I failed to overlook is that another theorem is the imaginary zeros theorem. So the imaginary zeros theorem says that non-real zeros or imaginary zeros come in conjugate pairs. So like if 4i is a 0, then its conjugate is also a 0, namely -4i. I'm gonna stop right here because my kids are crying. Okay, and we're back. So let's do this. So the directions from coming back from the break, we are asked to identify the degree, and then we're asked to spit out all the zeros, real and imaginary, and indicate if their multiplicity is greater than 1. In terms of indicating their multiplicity of greater than 1, that is something that you're supposed to always do. But since today is the first day that we talk about multiplicity, this is why we put that part in the direction. So the zeros, I'm just going to spit them out or write them in the order that we found them, writing them without the plus or minus notation. So 1 0 is -1/2. Another 0 is 5 with the multiplicity of 3 because it appears or recycles 3 times. Another one is -3 with the multiplicity of 2. And then another one is positive 4i, and then -4i. So remember, we always submit our answers without the plus or minus notation because we need to make sure that we understand that this represents 2 distinct solutions. Textbooks usually, from what I've seen, always write it with the plus or minus because they want to save on ink. That's my theory. Cool. For the grand finale, what is a degree? So I'm going to tell you how to find it in 2 ways. If and the only reason why I'm giving you 2 ways is because we're asked to find the zeros. One of them is just for you to count the number of zeros. So we have 1 0 from -1/2. We have a 0 of 5 with multiplicity of 3, so it's going to be 3 more zeros. So I feel like I'm back in kindergarten. Then we have a 0 of -3 with the multiplicity of 2, so it's 2 more zeros. And then we have a 4i, 1 more 0, and then -4i. So because we have 8 zeros, then that means that the degree should be 8. Now the question is, do we have to find the zeros in order for us to find the degree? No, you can just look at the highest exponent on any of the variable terms. But in this case, I really can't say what's the biggest exponent because this is not an expanded form. We have a product of factors. So like, let me go ahead do a side example. So if we had say p of x equals say x squared minus 2x plus 1, then I can say, okay, what's the degree? Okay, it's the biggest exponent on any of the variable terms, so the degree would be 2. Now, what if I had said p of x equals x minus 2 times x minus 3? So we can FOIL it out if we like. If when we do that, will give us x squared minus 5x plus 6, and then I can be like, okay, the biggest exponent is 2, so the degree is also 2. But it is not necessary to expand it on. What you can do, if you have a product of factors, you can just add the exponents. So the degree is 1, the degree is 1, and then we'll add up the exponents. Okay, and that will give us 2. So we get the same answer whether we expand it or not. So for our problem, let's go ahead add their exponents. It's pretty much the reason why we add them is just because it comes from multiplication. Like when we FOIL, x times x will give us x squared. Okay, so let's go ahead find the degree. So we're gonna go ahead add up all the exponents. So let me just write that on the side. So the first exponent is 1. The next exponent, I want to say 1, but we have a multiplicity of 3, so it's like x minus 5 times x minus 5 times x minus 5. So that's gonna give us 3 of them. Okay, so in this case it's gonna be plus 3 times 2 more factors. So the degree is 1, but with the multiplicity of 2, so that's gonna give us 2 more. Okay, and then the next one, the exponent is 2, and if I know how to count, 1 plus 3 is 4, plus 4 more is 8. Okay, so we get the same answer regardless of how you do it. So it may not be a bad idea to identify the degree from the start. That way you can be like, oh, the degree is 8, then we're expected to have 8 zeros. Do we have 8 zeros? Oh, we do? Okay, then we nailed it. Okay, so what are we gonna do next? So we had talked about multiplicity. Now we're gonna look at the zeros of a polynomial with odd and even multiplicity, and that'll be the end of this video. Okay, so let's do this. So recall from a previous unit. So let me go ahead, I cut and paste. So we have some polynomial function of degree n. Okay, so the degree is n. What is so special about the graph of this polynomial? So if the degree is n, then we're expected to have at most n real zeros. Okay, well, if the degree is n, then we're expected to have at most n real zeros. The real zeros are the x-intercepts. Okay, so if the degree is n, then we're expected to have at most n real zeros, or n number of x-intercepts. And if the degree is n, then we're supposed to have n minus 1 or 1 less turning point. Okay, so turning point, straight definition, is the point where the function changes from increasing to decreasing. Okay, in English, it's like those highs and lows. Okay, so whatever the degree is, you're supposed to have 1 less turning point. Okay, so let's do this. So before we look at the next fun problem, let's look at the zeros of even or odd multiplicity. If we have a 0 with odd multiplicity, so meaning 0 with multiplicity of 1, 3, 5, 7, 9, so forth, then in this case the graph will intersect the x-axis at whatever that 0 is. However, if we have a 0 of even multiplicity, so like 2, 4, 6, 8, and I feel like saying, who do we appreciate? Sorry, bad dad joke. Okay, so if we have a 0 of even multiplicity, unfortunately the graph will not intersect the x-axis at that 0. New to your life, we're gonna say that the graph is tangent to the x-axis at that 0. So tangent means that it touches the tangent to the x-axis means that the graph will touch the x-axis at that point, and that's it. In semi-English, it's gonna bounce off, you know, so that's it. So touch and go. It's like saying kiss and say goodbye. Okay, so 0 of odd multiplicity, we cross the x-axis. 0 with even multiplicity, we're tangent, so we touch only at one point, so we kiss and say goodbye. Okay, so let's look at the first fun problem, or the next fun problem. So it says the graph of a polynomial function p of x is given. That's nice. What is the minimum degree of the polynomial p of x? So what I'm going to do is identify how many turning points do we have, or how many hills and valleys should we have. Let me just go ahead and make those points. Okay, so we have 2 turning points, or 2 highs and lows. So if we have 2 turning points, then the degree should be 1 more. So namely 2, so the degree should be 1 more, or 3. Now let me take our answer and see if it makes sense. Whatever the degree of the polynomial is, we should have 1 less turning point. So if the degree is 3, then we should have 2 turning points. Do we have 2 turning points, or 2 highs and lows? Yeah, 1, 2. Okay, cool. So we did it. So now the question is, find the real zeros, write their multiplicities. I'm pretty sure I meant to write a word and. Okay, find the real zeros and write their multiplicity. So the real zeros are the x-intercepts. Okay, so we're gonna have a real zero at -2, and then we have 1 at 1, and then at 3. Okay, so the question is, if I follow the directions, I guess I should say we have a 0 of -2 with multiplicity of 1, but this is more meant like find the real zeros and write their multiplicities if higher than 1. It's just we don't have the space to write it. Okay, so that's it. If the degree is 3, then we're expected to have 3 zeros. Cool, we got our 3, so we're good. Now it says find the polynomial p of x that has the zeros and multiplicities from part B. Leave answer in factored form. So I know you're on it and you can go straight to answer, but I'm going to try to break it down for you. So I'm going to go ahead, list the zeros, but like separately. So x equals, let me just write it. So we have x equals -2, leave a space, x equals 1, x equals 3. Okay, so if these are the zeros, what were the corresponding factors? So let's go ahead, set each equation equal to 0. So for the first one, when we add 2 to both sides, that's going to lead to a factor of x plus 2. The second one will lead to a factor of x minus 1, and the third one will lead to a factor of x minus 3. Okay, so we want to tell the world, the graph of this polynomial should be given by whatever you want to name your function or polynomial. Our book is using p of x, I guess, for polynomial, but if you're like, no, me and f of x are friends, then go ahead, write f of x. So the f of x, so the polynomial is given by the product of what these should, of these I'm trying to find my words. The polynomial should be given of what these, okay, I can't find the words, I'm gonna say it like this. These should be the factors of the corresponding polynomial. Okay, so we have x plus 2 times x minus 1 times x minus 3, and you need to trust yourself. And in case you're having a moment, just ask yourself, if this was the question, what would be the zeros? Like, oh, this leads to a 0 of -2. This leads a 0 to +1. This leads to a 0 of, where am I? 3. Okay, so we nailed it. Now, if you would like to check your answer, go ahead. We're not going to do it though. You can go ahead, graph it and see if it looks like this. You know, do we have this action going on? And do we have these zeros at -2, 1, and 3? Fantastic. So what are we going to do for the third and final problem? Same exact thing. It's just I made it a little bit spicier. I made some of the numbers are going to look kind of the same to highlight the difference. Okay, so let's do this. Let me zoom in. So it says, what is the minimum degree of the polynomial p of x? So first I have to identify how many turning points we have, and then we know the degree should be 1 more. So we have a low point here, a high point here, and a low point here, or I can say turning point. since we have 3 turning points, then the degree needs to be 1 more, minimum degree. Okay, then the degree, we have 1, 2, 3 turning points, or 3 highs and lows, so the degree needs to be 1 more. So we're gonna say the degree is 4. Now, if you wanted to do it backwards, if the degree is 4, how many turning points should we have? With degree is 4, we should have 1 less turning point, so 3 of them. 1, 2, 3. Nailed. Now it says find the real zeros and write their multiplicities. I'm going to read it how it's supposed to say. Find the real zeros and write their multiplicities if higher than 1. Okay, so the real zeros are the x-intercepts. Okay, so the x-intercepts are the same ones, -2, 1, and 3. Okay, so we have x equals, where am I? -2, 1, and 3. Check it out. If the degree is 4, then we're expected to have 4 zeros. This is not 4 zeros, so we need to spit out a 4th zero. Let's go ahead and analyze the graph. Okay, now let's talk about the even and odd multiplicities of a zero. If a zero has an odd multiplicity, then the graph is going to intersect the x-axis at whatever that zero is. If the zero is of even multiplicity, then the graph is not going to intersect the x-axis. It's going to be tangent to the x-axis. It's going to be tangent to the x-axis at that point or at that zero. So remember, tangent, it touches only this x-axis at one point. So in English, it kisses and says goodbye. Okay, don't tell my boss I say those words. All right, cool. So our zero at -2. So what I'm going to ask myself, is the multiplicity gonna be even or odd? So I'm gonna ask myself, does the graph intersect the x-axis or is it tangent? So in this case, the graph intersects the x-axis, so the multiplicity has to be odd. Okay, so at minimum 1. Okay, why minimum? Because we want the smallest degree possible. The zero at +1. Okay, so I'm like, okay, should the multiplicity be odd or even? The graph intersects the x-axis, so the multiplicity should be odd. So 1, 3, 5, minimum 1. The zero at 3, so I'm like, okay, does it cross the x-axis? And no, it does not. The graph is tangent to the x-axis at 3, so the graph touches the x-axis only at one point. So in this case, the multiplicity has to be even, minimum of 2. Okay, so we're gonna say that 3 is a 0 with the multiplicity of 2. That's his minimum, but whatever, I can't fix it. So let's see if we need to bump up the multiplicities of any of these zeros. So again, we had said that the degree is 4. So if the degree is 4, then we're expected to have 4 zeros. So we have 1 from -2, another one from 1. Let me do my tally marks. 1 from -2, 1 from +1, and 3 is a 0 with the multiplicity of 2. So there's 1, 2. That's a grand total of 4. So we nailed it. So now let's go ahead find the polynomial for this bad boy with these zeros. So I'm gonna do it the same way we did it earlier. We're gonna highlight each zero, give it its own spotlight. Okay, so we have, where am I? So we have x equals -2, x equals 1, x equals 3, but let's give a special shout out with the multiplicity of 2. So if -2 is a 0, what will be the corresponding factor? If -2 is a 0, then the corresponding factor should be x plus 2. If 1 is a 0, then the corresponding factor should be x minus 1. And if x equals 3, or if 3 is a 0, then the corresponding factor should be x minus 3. But bear in mind that because the multiplicity is 2, it should actually be the square of x minus 3. So in this case, if -2, 1, and 3 are the zeros, then the corresponding factors are x plus 2, x minus 1, and the square of x minus 3. Let's go ahead and multiply them to form that product. Cool. So now the question is, if you wanted to check it, how can we check it? Plug it into your calculator, you know, y1 equals, and then you can confirm that you're gonna have the zeros of -2, 1, 3, 3 with the multiplicity of 2. How can you tell? Well, the graph should be tangent to the x-axis of at 3. Okay, cool. So we did it. Thanks, guys.